Now we switch to share screen, the usual routine. Okay. Hopefully this will work without trouble. All right. Okay, good. So I got my kind of beat up piece of paper here. This is a bit of a summary from last time. Yeah, so let me just go over some of the things we ended up with in the end of the hour last time. One of the problems we examined was a simple one-dimensional scattering problem. This is where a wave comes in from the left. Actually, on the potential curve, it climbs up, particle climbs up the curve, reaches a turning point, and goes back out. So in quantum mechanics, there's an incident wave and a scattered wave coming back, reflected wave coming back. Here's a turning point. So we analyzed this problem by requiring that the wave function in region 2, the classically forbidden region, should decay exponentially. And that gave us a connection between the coefficients of the incident wave and the reflected wave using the connection rules, which I presented as a series of matrices. And by the way, this is the phase space picture of the same thing. The incident wave comes in along the orbit here with positive momentum, reaches the turning point, and goes back out with negative momentum. In any case, the net result of that analysis is the wave function in region 1, which is a classically allowed region, is a sum of two waves. The first one is the incident wave, that's the upper one. And the second one is the reflected wave, that's the lower one. They've got this action function S of x in it, and there's a phase shift. The S of x is defined as the integral of p dx, but we need to choose an initial starting point. So we'll choose that to be the turning point, just because it's kind of the obvious choice here. And what that means is that S of x is negative and increasing as we move in like this towards the turning point. So this is actually negative and increasing to the right. The fact that it's increasing to the right means the wave is propagating to the right. Okay. Now there's an intuitive idea that's one of the lessons of this analysis, by the way, is an intuitive notion which is useful for other problems. And that intuition is this, is that as the particle moves along its classical orbit, you can imagine that it has a little integrator on it, and it's integrating p dx to accumulate a phase S of x. And so that determines the wave of the quantum wave function that's being carried forward by the particle. Now, in the neighborhood of the turning point, the actual concept of the WKB phase loses meaning because the WKB approximation breaks down. But in a certain sense, the particle doesn't know that. It just continues to integrate p dx. In fact, as a function of time along the orbit, you can consider this p dx, as I say, as a function of time along the orbit, call it the function S of t. If we make t equals 0, the turning point, so that S of t vanishes there, then S of t is actually equal to S of x on the upper branch, where it's negative, and it's equal to minus S of x on the lower branch, where it's positive. So basically, the just p dx just keeps increasing as a particle moves along its orbit like this. By the way, the p is positive here and the dx is positive on the upper part. So p dx means s is increasing. When you come to the lower branch, the momentum is negative, but the dx is negative too. So p dx continues to increase. And that's why you get this positive phase here. In any case, as I said, in the turning point region, the phase actually isn't defined, but the classical particle goes right through it and comes back out again. And when it emerges back out to where the phase is defined, it's got this phase that it accumulated in doing its little integration along the orbit. But in addition, there's a phase shift of pi over 2 that came from its experience in this region where the phase wasn't defined. So one of the ways of saying this is that a WKB wave suffers an extra phase shift of pi over 2 on passing through a turning point. That's just an intuition about how it works. The actual getting that pi over 2 involves some analysis. This, by the way, the turning point, by the way, is an example of a focus. It's kind of a one-dimensional version of a focus. Technically, it's called a caustic. And phase shifts like this occur in other problems. For example, if you have an ordinary lens, and you focus the light, like you do with a lens on a point. Of course, it's not perfectly a point because of diffraction. If you look at the wave field that goes into that focus and then comes out the other side, what you'll find is the wave field emerging from the other side of the focus is actually shifted by a phase of pi relative to the phase of the waves that came in. That follows from a detailed wave analysis of the optics. The reason it's pi instead of pi over 2 is because it's a two-dimensional problem. The lens is focusing a family of rays that's two-dimensional, and this is only one-dimensional. That's the reason for it. But the basic phenomenon is the same as this pi over 2 phase shift that you see here. All right. In any case, that leads to an intuition then about how phases accumulate as particles move along their orbits. And that's useful for a quick and dirty understanding of oscillators. So if we have an oscillator, which is the next problem we turn to, you really have three regions. You've got two classically forbidden regions outside the two turning points and a classically allowed region in the middle. And you can use the connection rules at the two turning points to work out all the details of the wave function and stuff. But if you do all that algebra, what emerges is a simple condition. It's a quantization condition. And it works like this. If you take any point on the orbit, like let's say right there, as the particle moves along, you can imagine it accumulating a phase, which is the integral of p dx. And it continues to do this until it goes around and comes back to the initial starting point. And when it does, the total accumulated phase is the loop integral of p dx divided by h bar. That's what that phase is. Now, the loop integral of p dx, by the way, is the same thing as the area of the orbit. So that's an interesting geometrical interpretation of that. But it's really nothing but just continuing integrating p dx around the orbit. However, it also passed through two turning points, one there and one there. So there's a phase loss of pi over 2 for each of those two turning points. Now, the total phase, including the integral p dx and the phase loss going through the turning points, when you come back to where you started from, has to be an integer multiple of 2 pi in order that the new wave function that you find there is in phase with the old wave function that you started with. Otherwise, otherwise the wave function interferes destructively with itself. And so this gives a quantization condition based on an integer n, like this. Now, as I mentioned, this integral, loop integral, is the area. And so if I just solve for the area, I get this equation. The area is equal to loop integral p dx is equal to n plus a half times 2 pi h bar. That's just doing the algebra to solve this equation. Plus a half came from this minus sign here, which I brought over the other side. So this is a way of saying that what we call the quantized orbits are orbits whose area is equal to n plus a half integer, multiplied times this unit of area here. This unit of area, by the way, is called a Planck cell. A Planck cell, in 1D anyway, a Planck cell is just a region of phase space whose area is 2 pi h bar. By the way, 2 pi h bar is the same thing as Planck's original constant h that he used in, he wrote it as E equals h nu instead of h bar omega. Anyway, that's what it is. I'll just write it as 2 pi. But that's what it is. It gives you an area of a cell in phase space. All right. And this quantization condition can also be expressed in terms of the standard definition of what they call the action of the orbit in classical mechanics. It is important that the orbit depends on the energy E, and so the area does also. So this gives you the area as a function of energy is given by this n plus a half quantity over here. And that in turn defines the nth energy eigenvalue. The nth energy eigenvalue is 1, for which the area has this quantum value, has this quantized value n like this. And so this gives us what we call the Bohr-Sommerfeld, this is Bohr-Sommerfeld quantization that gives us energy eigenvalues in terms of the action integrals. All right, so it's this counting of phases at turning points and so on is one of the main reasons I wanted to bring that up. Now I see that I used up not only a preview time, but also getting to real time. But anyway, that's some of the background of what we did last time. Are there any questions about that before I proceed with new material for tonight?
I had a question.
Yes.
Where does the 1/2 come in from if the pi over 2 is being multiplied by 2 from going through two turning points?
Yeah, well, 2 times pi over 2 is pi, but there's 2 n pi over here. So it brings a half of an n pi, a half of 2 n pi. That's where that came from. It's just doing the algebra of combining pi here with the 2 n pi over there.
Oh.
Okay, see the 1/2 times 2 pi is just pi. That's what that is.
Oh, okay.
Yeah, that's all it is. It's just doing the algebra. Okay, all right. Now, In the last lecture, I actually worked this out for a harmonic oscillator, and we found that we got the exact energy eigenvalues. I'm going to start tonight with another problem too, another simple problem. We'll take the case of a particle in a well like this. So let's plot the, as a function of x, let's plot the potential energy V of x. It's infinity outside the well like this. Let's say the well has a length of L like this going across. That's the width of the well. The potential is infinity over here too, like this. If we plot the phase space diagram for the particle in the well, oh, by the way, in configuration space, what the particle does, of course, is it just goes across, bounces, and comes back. It's just an orbit that bounces back and forth like that. That's the classical orbit. If we look at it in phase space, I'll draw the position and momentum variables like so. And I'll draw the L barrier here like so. And the particle going to the right, it's got a constant momentum like this. Let's call that momentum P naught. Actually, P naught is related to the energy by the square root of 2me. And then when the particle reaches the right wall, it reflects, and so the momentum changes sign, so it comes down here and moves back like that. So if you like, the phase space orbit moves across like this and instantaneously jumps down to this lower point, then moves back here and then instantaneously jumps up like that. So the orbit in phase space is a rectangle. So what's the quantization condition? Well, it should be 1 over h bar integral, loop integral of p dx. That's the phase accumulated by the particle. Minus 2, because there's 2 turning points here. But now instead of pi over 2, we have to have a phase of pi for each turning point. The reason we have pi here is because this is a hard wall. You have a phase shift of pi over 2 in the case of a potential, which is a soft wall, which is on the last page that I put up. And that involves the analysis of the area function and so on. But a hard wall is a different analysis. The reason the phase shift is pi is because the reflected wave, well, it's because the boundary condition at the wall is the wave function has to be 0. So the sum of the incident wave and the reflected wave has to vanish there. So a pi means z to the I pi, which is -1. And that's just the minus sign that makes the two waves cancel at that given point. Anyway, so the point here is that a hard wall is a different phase shift. But in any case, this still must equal to 2n pi. And so if I solve this equation for the area, then what I find is that it's, instead of being n plus a half, it's n plus 1 times a Planck cell 2 pi h bar. In fact, let me write capital N is equal to n plus 1 here, just for abbreviation. So this is capital N times 2 pi h bar. Now, on the other hand, the area is just the width times the height. Oh, by the way, this was minus p0 coming back. So the height is twice p0 in phase space, and the width is L, which is the size of the box. And that's the same thing as 2 times the square root of 2me times L, like so. And I want to solve for the energy E, so let me cancel the 2 there and the 2 there. And if I just solve for do the algebra to solve for energy E, we get E is equal to capital N squared, pi squared, h bar squared. I'm squaring both sides, square that side. And then it's divided by 2m times L squared, like so. And lo and behold, this is the exact energy levels for the particle in the box, exact quantization. The WKB wave functions are exact too. So in this case, WKB theory is exact. Now you might say, okay, big deal. WKB theory gives us the exact answer for the eigenvalues for both the harmonic oscillator and the particle in the box. These are both fairly simple problems. Let me show you now some of the things that WKB theory can be used for that are not quite so trivial. To begin with, let me introduce what I call the number of states. I'll call it N here, number of states, to write it out in words. What's called the number of states is a function of energy, N of E. And it's simply defined as the number of energy eigenvalues E sub n, which are less than or equal to the given energy E. It's just the count of energy eigenstates that lie below a given energy E. Now, this is something that's oftentimes important in application. So let me say some things about this N of E function. If we plot N of E as a function of E, the function is actually a step function. It's 0 before the ground state energy. Then it rises by 1 at the ground state energy. And then it's 0 until you come to it stays at 1 until you get the next energy level and goes up by 1. There might be different gaps between how far apart the energy levels are, short and long. You might have a twofold degenerate energy level, which means it jumps up by 2 and so on. It goes up like this. So anyway, it's a step function. It looks something like that. Now, what I'm going to be talking about tonight is a smooth approximation to this function n of e, which is oftentimes all you need for practical applications, especially when the energy gets to be large and these energy levels start to become very close together. If I go back to the Bohr-Sommerfeld quantization condition for a one-dimensional problem, you can see that the amount of phase space area was measured in terms of Planck cells is n plus a half. If n is large, and we're going to be talking about large quantum numbers here tonight in this next phase here. So if n is large, then you can more or less ignore the half, and you can say that, roughly speaking, is a good approximation anyway, that that each quantum state occupies an area of a single Planck cell. Yes, was there a question? Okay, so each quantum state occupies an area which is a single Planck cell. And so what this tells you then is the number of states n of e is equal to the area of a Planck cell, which is 1 over 2 pi h bar, times the integral around the orbit, where the orbit has energy e. This is a classical orbit now of pdx, like so. All right. And this is valid when n is large. N is large, is the large, because we're ignoring the 1/2. This is an asymptotic formula. Okay. Let's play some games with this formula. Here's one of the things to say.
Sorry, just a question. So I thought n of e was the number of states that are less than energy e, but wouldn't that, what you've written, just give you the number of states at an energy e, or there's something I'm missing, I think?
No, because the nth quantized orbit, see, this is counting the number of quantized orbits that lie below a given energy e. Well, the nth so if I think of it this way.
Oh, I see. Yeah.
You see, okay. You've got a series of quantized orbits in here.
Yes.
And the area in the annular region connecting each one quantized orbit to the next one is a Planck cell. The only difference is that the lowest orbit has an area of just 1/2 of a Planck cell. But for all the others, the increment is 1 full Planck cell. So if we count the number of Planck cells inside the classical orbit, that gives us an estimate of the number of quantum states whose energy is less than the energy of that classical orbit. Okay, now let's look at this. Let's look at this integral here. If I sketch the phase space orbit again, x and p, let me do it again like this, something like this. The orbit itself is h of x and p is equal to the energy e. On the other hand, the interior of the orbit is where the h is less than, it's where e is less than h. Less than h is the interior. And the exterior is where e is greater than h. This is for the regions in phase space. And so we can rewrite this formula in the following way: as 1 over 2 pi h bar times an integral, which is taken over both x and p to give the area, but it's taken over the region where h of x and p is less than or equal to the energy e. Okay. And this is a useful formula for one-dimensional problems for calculating the number of states. Actually, what's even more interesting about this is that this formula generalizes in the obvious way to multidimensional problems. In multidimensional problems, let's do this. Let's take our variable x and let's replace it by, I'll call it x1 out to x sub f. And the momentum p will do the same thing as p1 out to p sub f.
In the integral, is that supposed to be p dx, or are we doing an integral over p?
No, this is a two-dimensional integral over both x and p. In other words, this is an area integral, but it's taken over the region where h of x and p is less than e. So
okay, I see.
That's the interior of this, and that's the same as this loop integral here. Actually, if you know the truth, to tell you the truth, this is actually an application of Stokes' theorem to take you from a 1D integral around a boundary into an integral over the interior. But it's also pretty clear that this is the area inside that region. All right. In any case, let's go to a multi-dimensional.
And this equation is taking into account the possible degeneracies.
The possible which?
Degeneracies, the degeneration of the state, the possible degeneration of states.
Well, in a 1D problem like this, there wouldn't be any degeneracies because in one dimension, the bound energy eigenstates are non-degenerate. In multi-dimensions, yes, it would be taking into account the degeneracies. Even counting degeneracies, each quantum state occupies a single Planck cell. So in multi-dimensional problems, you have to count the degeneracies. All right, in any case, let's go to a multi-dimensional notation here where X and P get replaced by F, let's call them F-dimensional vectors here, where F stands for what we call the number of degrees of freedom. That's the usual meaning of degrees of freedom in mechanics. If I can spell it right, freedom. I can't spell it right while I'm writing. All right, so let's make it multi-dimensional like this. Then it turns out the formula is still valid. It's only an asymptotic formula and it's not exact, but it's, so let me make it an approximate. But it's given by, and by the way, the single Planck cell in many degrees of freedom is equal to the quantity 2 pi h bar raised to the F power. It represents a volume of phase space you see for F degrees of freedom. This pen is looking bad because it's out of ink. Let me get another pen here. All right, so then the number of states then is given by 1 over 2 pi h bar to the F power. That's a Planck cell in F degrees of freedom. An integral dx dp, where it's now understood these are F dimensional integrals like this, taken over the region h of x and p is less than the energy E, less than or equal energy E. And that's it. That's just a generalization of this formula up above here like this. Let me box it because this is what we get here for this estimate. Now, I'd like to give you an example of how this works out. Multi-dimensional example. Let's take the case of a particle in a box in 3 dimensions. So let's do 3D space here. This is not a 1D problem anymore. Let's do 3D space. Let's have some kind of a region and we can make it lumpy like this. So region R, let me call it script R like this. That's what this is. It has a certain volume. And what we're going to do is we're going to imagine a particle in a box where the box has that shape. It's not a square box anymore. And let me get this out of the way. And the potential energy is going to be this, is that V of X is equal to 0 if, I'll write it as X vector, you see, because it's 3-dimensional space now. If X is contained in the region R, and it's equal to infinity if X is not contained in the region R. So in other words, it's a hard wall at the boundary. That's all that means. This also means that the Hamiltonian h of x and p, and this is a classical Hamiltonian now, is equal to p squared over 2m if x is contained in R, and it's equal to infinity if x is not contained in R, because it's kinetic plus potential, which is infinite there. All right. So let's work on this integral then. 1 over 2 pi h bar, here we have f equals 3 because we're talking 3-dimensional space. 2 pi h bar cubed, we have the integral d cubed x d cubed p. It's a 6-dimensional integral over the region h of x and p, these are vectors now, is less than or equal to energy E. This is what we need to evaluate here, this integral. This is going to be our N of E. Well, this we can work out. We do it this way. Let me copy the 1 over 2 pi h bar cubed. The integral over x d cubed x. You see, if x lies outside the region R, then the Hamiltonian is infinite. So that's not part of the region we need to integrate over. So this x integral only needs to be taken over the region R. If x is inside the region R, we do the momentum integral. And in that case, the Hamiltonian is p squared over 2m. So this needs to be taken over the region of p squared over 2m is less than or equal to the energy E. Well, that region, you see, is the same thing as the region in which the magnitude of the momentum is less than or equal to the square root of 2me. Like that. That's what that means. So what we've got is an integral which the x part only runs over the box, and the momentum part runs over what you can see as a sphere in momentum space whose radius is given by this quantity here, magnitude of p. So the momentum integral is easy to do. It's 4 pi, it's the volume of a sphere, it's 4 pi over 3, and this is the radius. We cube that, we get 2me to the 3/2 power. as far as the integral over x is concerned, that just integrates into the volume V, which is the volume of the box. I didn't say that, but let's say this is volume V here for this box. Let's call it that. So I'm not to be confused with potential. I'm sorry about the notation there. But in any case, that's the volume V. And so if we put this all together, what we get is that N of E then is the volume of the box divided by 2 pi h bar cubed times 4 pi over 3 times the quantity 2me to the 3/2 power. And let me box that because that's the answer. This is shows you how easy it was to obtain this asymptotic estimate for the number of states, free particle states inside a box of now of more or less arbitrary shape in 3 dimensions. Now, an associated quantity that we're oftentimes interested in is the derivative of the number of states with respect to energy. This is called the density of states. And if you've done any physics at all, you've certainly heard about density of states. Well, here we just get it by doing the differentiation. It's just a simple algebra to do it. So it gives you 4 pi m times the square root of 2me like this. And let me box that because that's also a useful formula. This final formula that I've derived is the density of states for free particle solution, quantum states for free particle solutions inside a box. And it is this formula is usually derived in courses on stat mech where you need it for many purposes. But there the derivation involves setting up a box and looking at the exact energy eigenfunctions in a box. What this derivation shows you is that the same answer holds even for a lumpy container which doesn't have any particular symmetry. And in fact, the only place where the geometry of the container enters is in the volume factor that occurs right there. This is not an exact formula, and there are higher order corrections. It turns out the higher order corrections involve the geometry of the box in a more complicated way, the surface area and things like that. But the leading term involves only the volume, and it agrees with the formula you get for a square box. All right, so in any case, this is an example of a derivation of an important quantity which appears in physics, the density of states per unit energy interval, using this asymptotic rule. All right, basically, the basic idea lying behind this is that each quantum state occupies a single Planck cell of phase space. That's a classical or semi-classical interpretation of quantum states. All right, now, I'm not quite done with this. I want to say something else as well. There's this formula that I had up above right here. This is the 3-dimensional version of it. This can be expressed in fact, let me go back to the more general version, which is here. Here's the more general version for F degrees of freedom. There's another way to write this, which is oftentimes useful, and involves introducing the Heaviside step function. The Heaviside step function is a function theta of x, which is given by 0 if x is negative, and it's given by 1 if x is positive. It's kind of a standard function, and if you plot it as a function of x, theta of x is 0 on the negative axis. It hops up to 1 at x equals 0, and then it's a straight line going across like that. So it's a step function. It has the property that its derivative ddx of theta of x is a Dirac delta function, delta of x. You can see this because if I take the derivative is 0 for negative x and it's 0 for positive x, but right where that line goes up, you have the narrow delta function there. This is basically delta of x is being plotted here. All right, so theta of x is actually the indefinite integral of delta x from minus infinity to x. If the upper limit is less than 0, then the answer is 0. But if the upper limit is greater than 0, the answer is 1. And that's what you got here. All right, in any case, this is the theta of x, the theta function, or the Heaviside step function. Now, this has the property that if I consider theta of E minus h of x comma p, this is equal to 1 in the interior, where the energy is less than the Hamiltonian, and it's equal to 0 in the exterior, where the energy E is greater than the Hamiltonian. And so, yes, question.
For when you wrote the theta of x, the step function you wrote x greater than 1 and x less than 0.
Thank you. This should have been 0 here. Thank you. Thank you for pointing that out. Yeah, so by using the theta function, we can in effect set up, this is called, mathematicians call this the characteristic function of the region. It's just 1 inside and 0 outside, but we can write it in terms of the theta function, which is useful. So what that means is that in this formula here, where we want to integrate over the region where h of x and p is less than e, I can now rewrite that formula in the following way, giving us the number of states. Now this is again for a multidimensional problem, is the integral of dx dp, both are f-dimensional integrals, divided by the 2 pi h bar normalization, 2 pi h bar to the f power. And now what I have is the Heaviside step function, theta of e minus h of x and p. This h of x and p is the classical Hamiltonian, you see. And now the integral is taken over all of phase space. So this is a 2f dimensional integral. Could be potentially a high dimensionality to do this integral, but this is what we get. All right. Now then, to get the density of states, then you see the only energy dependence is right there in the theta function. So this becomes an integral dfx dfp over the same normalization 2 pi h bar to the f of a Dirac delta function now of energy minus h of x and p, like so. And what you can see then is the density of states in quantum mechanics, the number of states that increase with a small increment in energy, is related to the amount by which the energy shell in phase space, in the 2f dimensional classical phase space, increases when the energy increases. A little delta function right there at the surface of that what you'd call the energy shell. All right, now let me show you an application of this. In statistical mechanics, the partition function z of beta is given by the trace of e to the minus beta h, as I've explained earlier in connection with the density operator. And this in turn can be written, if you evaluate this, the trace in the energy eigenbasis, this can be taken as the sum on n of e to the minus beta e sub n, like this. It's just the sum of the Boltzmann factors, 1 for each energy level. Okay, let me kind of reset this to see if I can make this brighter here, a little more clear. All right, if there's degeneracies, we just simply repeat the E sub n's for different values of n. You know, E1, E2, and E3 could all have the same energy. So this formula is valid even in the case of degeneracies, if you understand what I mean by the n counting of the energy eigenstates. Now, if you have any system, any quantum system that has more than about 1 or 2 degrees of freedom, it doesn't take very many. And if you go to an energy that's reasonably above the ground state, it doesn't have to be very far. What you find is the density of states gets really big. It grows exponentially with the number of degrees of freedom, even more than that, faster than exponential with the number of degrees of freedom. And so what this means is that under those conditions, it's quite reasonable to replace this discrete sum by an integral, which is an integral over energy E of the density of states dn dE times e to the minus beta E. So this is not E sub n any longer, it's a continuous variable of integration. The upper limit obviously should be infinity because you want to count all states. If we count the density of states as being 0 below the ground state, which is reasonable, we can take the lower limit down to minus infinity without changing anything. So let's do that, that understanding of dn dE, okay? Now, if I then plug in my formula for dn dE from above, let me bring it down like this, into this slot right here, then what we get is that we get the partition function z of beta is equal to integral minus infinity to plus infinity over energy E times e to the minus beta E, taking that factor of that integral. And then for the dn dE, I'll plug in this integral, dfx dfp divided by 2 pi h bar to the f, times a Dirac delta function of E minus h of x and p. And now what you see is that you can do the energy integral because of the delta function. And it turns into the integral over all of phase space, dfx dfp over 2 pi h bar Planck cell to the f power times e to the minus beta times the classical Hamiltonian h of x and p. And this is the classical expression. This is now the classical Hamiltonian. I want to emphasize that. We started up here with the trace of this. This was the quantum Hamiltonian. I put a hat on that just to emphasize that. This was the quantum Hamiltonian. But through this sequence of asymptotic approximations, it's expressed now in terms of the integral of e to the minus beta h, where h is the, I'm sorry, that's the quantum Hamiltonian. This is the classical Hamiltonian. So this is the classical approximation for the partition function, which is quite useful in statistical mechanics. And it was actually known to Boltzmann before quantum mechanics was even invented. Of course, he didn't know about h-bar, so he didn't know about this normalization factor, but the rest of it he knew about. And he understood that that was a formula for the partition function. All right, so that's a kind of an end of what I want to say about WKB theory and various semi-classical techniques. Are there any questions about that before I move on to the next topic?
Yeah, so is DNDE a classical approximation? That's the one that we have here because it's in terms of h of x comma b?
This would be a classical or semi-classical approximation to the density of states. Yes, that's
Okay.
correct.
Thanks.
The real density of states is a sum of delta functions, because every time the energy goes up by 1 unit, you get a delta function. But if you've ever done condensed matter physics, you know that nobody ever uses that. Instead, they use smooth approximations to it. And these approximations here are very, very frequently used. Okay, no. All right. Then if there's no more questions, I'm going to move on to the next topic, which is.
Actually, could I,
yes,
do you mind if I backtrack just a little bit?
No, go ahead.
So this is regarding like the discussion about soft walls versus hard walls.
Right.
So I'm thinking like, what is the crossover point from soft wall to hard wall? Like, I guess in the limit that v of x, a dv dx goes to infinity, I guess.
So obviously that's a good question. You'd obviously have to analyze it in detail, and it has to do with the size of h bar and the range over which there's in effect, if the wall is not soft, there's a certain range over which the wave function dies off. And that requires a detailed calculation that I would rather not go into right now, but I'd be glad to talk to you about it in office hours if you want to.
Yeah, sure.
So
So
one can analyze that. There's a transition region as the wall becomes more and more stiff.
Oh, okay, yeah.
Okay.
I'm guessing during the transition region, the phase shift is somewhere in between pi over 2 and pi.
Yes, I would assume that too, but I haven't done the calculation lately, so I don't know how it works out.
All
yes,
right.
that certainly has to be true.
Right.
Probably what happens is that you can no longer use the asymptotic forms of the Airy functions. I mean, the Airy function is still a good approximation in a narrow turning point region.
Mm-hmm.
But if it's not wide enough, it's like h bar to the 1/6 or 1/3, I forget the power, is the width of the turning point region. And so that has to be compared with the range over which the potential is changing. So anyway.
So I'm not 100% sure where we had to use the approximation that dv dx is small in doing the WKB approximation.
dv dx does not have to be small. Okay, so v is a classical quantity, so dv dx is also classical. What do you mean that we had to assume that dv dx was small?
I mean, in the soft wall case, the potential doesn't change much.
Oh yeah. Okay, yeah, so I think that where that comes in is that when we did the analysis in the turning point region, we solved them in terms of area and Berry functions, and then we used the asymptotic forms of those functions to connect with the WKB solutions on the two sides. Now that's only valid if the turning point region is big enough for the asymptotic forms to be valid.
Oh yeah.
And I think that's where it comes in. I think that's where you'll see it.
Okay.
All right.
I see. Yeah. Thank you.
WKB theory is a very big subject, especially when you get into multidimensional things. And it gets into, I mean, some very sophisticated mathematics. Geometric quantization is in some sense a glorified version of WKB theory. So there's an awful lot, there's great depth to it, and one can go into this in much greater depth than I'm just covering some of the highlights in these lectures here. All right, so the next topic I want to address is harmonic oscillators, which you've all seen before. So I'm going to be brief about certain parts of it. But in any case, if I write down a mechanical harmonic oscillator in the usual notation, the kinetic energy plus potential energy, it looks like this, m omega squared over 2 times x squared, where omega is the frequency of the oscillator. I'm sure you all know that. Let me kind of make this line here a little more darker so to separate off the new stuff from the old stuff. The potential energy, of course, is a parabola like this. What that means is that at any, so this is V of x here, and this is x. At any energy E, there are classically forbidden regions, so the wave function has to die off exponentially outside the class, in those classically forbidden regions. What that means is the wave function is normalizable, and the wave function therefore belongs to the discrete spectrum. This is generally what you get with bound states. They belong to the discrete spectrum. Another thing too is that the eigenstates are non-degenerate. This is a general feature of one-dimensional potential problems, is that the bound states are always non-degenerate. This is actually proved in my notes number 6, is a very short set of notes on 1D quantum problems. I didn't lecture on it, but if you're willing to accept my word for it, it's true that they're non-degenerate. So the first thing we can say is just in the basic qualitative features of the potential, it goes to infinity and it's a bound states, is that the spectrum of the harmonic oscillator will be discrete and the energy eigenvalues will be non-degenerate. Now, having said all of that, I'm going to simplify things by using units and simplify the algebra certainly by using units in which h bar equals m equals omega equals 1. This saves an awful lot of writing and converts our Hamiltonian into 1/2 of x squared plus p squared, like so. So we'll analyze this Hamiltonian. I want to make some general comments about it. In the first place, let's look at this first place classically. I'm going to switch back and forth between classical and quantum analysis in the Hamiltonian. But classically, this Hamiltonian can be factored into 2 factors. One is x plus IP over the square root of 2, and the other one is x minus IP over the square root of 2. It's just the factoring of the sum of 2 squares into complex factors like this. So let's define a classical very complex variable I call x plus IP over root 2, and its complex conjugate, which I'll call z bar, which is x minus IP over root 2. I'll use the bar for the complex conjugate here, c and z bar. So this factorization of the classical Hamiltonian breaks it up into z times z bar, which is the absolute value of z squared. And this is worthwhile remembering this for a view of the classical Hamiltonian. Now these variables z and z bar are particularly useful for studying the classical harmonic oscillator. They simplify the equations of motion quite a bit, even though they're complex. And what they suggest is that the corresponding operators in quantum mechanics would be useful for the quantum problem. And this is exactly true. And I think you know where this is going because you can see it already. Let's now go to the quantum problem. The Hamiltonian formula looks the same. The Hamiltonian is 1/2 x squared plus p squared. I'm not going to bother to put hats on things because it takes too much writing, but I'll put a quantum next to it to indicate, which of the 2 interpretations we're using. But in any case, there's your Hamiltonian. Let's introduce variables a and a dagger. A is given by x plus IP over the square root of 2, and a dagger is given by x minus IP over the square root of 2. These are the obvious analogs of the z and the z bar of the classical motion. The x and the p, of course, have commutation relations, which is IH bar, except here we're setting h bar equals to 1, so the xp commutator is just I. And if you use this in the A and A dagger, you can compute the definitions of A and A dagger, you can compute their commutation relations, and AA dagger is a commutator of 1, like that. You can take the expressions for A and A dagger and solve for x and p in terms of them, and then substitute into the Hamiltonian. And if you do that, you express the Hamiltonian as a function of A and A dagger. And it turns out to be this, it turns out to be AA dagger plus 1/2. Another way of writing this is to say that it's 1/2 of A dagger A plus AA dagger. You can see that A dagger A or AA dagger is analogous to the classical expression, which is the ZZ bar, which is the magnitude of Z squared. Classically, it doesn't matter what order you put them in. Quantum mechanically, the order does matter. And by putting them in this order and dividing by 2, you see I get a manifestly Hermitian operator H. But by using the commutator, I can also write it as A dagger A plus a half, and that's going to be the form that I'll mainly use in this lecture tonight. So in any case, the 1/2 came from the commutators, the non-classical commutators that appear in quantum mechanics. I'll also write this in the form of n plus a half, where capital N is defined as A dagger A, and is called the number operator. And what I'm going to present for you is something I'm sure is a review for you, which is Dirac's algebraic derivation of the spectrum of the harmonic oscillator using algebraic techniques based on these creation and annihilation operators. We'll get the spectrum. You can also get the wave functions as well. Spectrum, of course, means the eigenvalues. So strategy will be to find the spectrum of N, and then the spectrum of H follows just by adding a half, because that's just a C number addition. As far as the wave functions, the energy eigenfunctions are concerned, the eigenfunctions of N and the eigenfunctions of H are the same. There's no difference between them. So let's work on the N here. Let's let nu be an eigenstate of the number operator N with eigenvalue nu, like this. I'm using the symbol nu here because I don't want to pretend that I know anything about the value of the eigenvalue, whether it should be an integer or a fraction or a positive or a negative number, anything like that. It does have to be real because the number operator is Hermitian, as you can tell by looking at it. But except for that, initially we know nothing about the value of nu. We do know, however, that the spectrum, as I said, is discrete, and so these states nu are normalized. And let's suppose we have normalized it, so that nu therefore is not equal to 0. It's a non-zero. This nu ket here is a non-zero vector. Let's make this assumption. All right, now then, we can immediately conclude that the eigenvalue nu must be non-negative. We do this by multiplying by bra nu on the left-hand side. So working on the left-hand side, we get nu sandwiched around N, but that's the same thing as nu sandwiched around A dagger A nu. And that's the same thing as the vector A nu as a vector squared. It's the square magnitude of the vector A nu. But putting the nu on the right-hand side, that gives us, quantum value, the quantum number nu, C number nu times the scalar product nu with itself, which is equal to 1. So it just gives us a nu like that. On the other hand, the square of any state vector in Hilbert space is non-negative. So this whole thing has to be greater than or equal to 0. And thus we conclude that the eigenvalues of the operator capital N must be non-negative. As we say, capital N is a non-negative definite operator. All right, so we're narrowing down the possibilities for the eigenvalues and having determined that they must be positive. Next, we work on some commutation relations. Let's look on the commutator of A with N. This is worked out by straightforward commutation relations, and I'll skip the algebra for it because I'm sure you can do it. It turns out to be minus, I better do it because otherwise I got it backwards. I think actually what I want is N with A, but let me do it. Let's work it out and we'll see. So this is going to be equal to A dagger A, which is N times A, minus A times A dagger A. Yeah, I think this is how I want to do it. Now let's take the second term here, and this A dagger will use the commutator up above and swap them. So the second term becomes minus A dagger A plus 1 times A, like so. And A dagger A is, of course, the number operator number, the number N, like this. So the A dagger A times A cancels this factor there. Those go away. And the result is this is just equal to minus A. So to summarize, I get a commutator of N with A is equal to minus A. Now, if you do the same thing with A dagger, you get commutator N with A dagger is equal to plus A dagger. Okay. Now then, so that's just working out some basic commutation relations of these operators we've defined. Now let me suppose that nu is an eigenket of N with some eigenvalue nu, which we now know is non-negative, and let's apply the A operator to it. And then let's multiply by the number operator N. Well, using the commutator, this is the same thing as NA. NA is the same thing as AN minus A, like this, multiplying onto nu. And now the capital N is adjacent to nu, and so it brings out nu. And the result is that this is nu minus 1 times A nu, like so. And so we have capital N acting on A nu is nu minus 1 acting on A nu. And this leads to a theorem, which is worthwhile stating precisely so you follow the logic of this. We say it this way, is if the vector A nu is non-zero, then A nu, the vector A nu, is an eigenket of operator N with eigenvalue nu minus 1. I have to put in the qualification if A nu is not equal to 0. We're assuming that nu itself is not equal to 0 because we assumed up here that it was an eigenstate. Where did I say it somewhere up here? That it's an eigenstate of a normalized eigenstate of capital N. So the state nu is non-zero, but that doesn't mean that A nu is non-zero. So I have to put in this qualification if A nu is non-zero, because if A nu is equal to 0, look, this equation is just saying 0 equals 0, and it doesn't tell us anything. Besides, eigenkets are normally supposed to be non-zero. Okay, now if I do the same thing with the creation operator, what we get is that if a dagger nu is non-zero, then a dagger nu is an eigenket of the operator N with eigenvalue nu plus 1. And of course, these are the raising and lowering properties of these two operators, which you're quite familiar with. Move my hand out of the way here. All right. Now to proceed, we need to decide when is it true, or is it ever true, whether A nu is equal to 0. Let's check that. So A nu is equal to 0 if and only if A nu squared is equal to 0. This is the property of the metric, you may recall, that we postulated for Hilbert spaces. A vector vanishes if and only if its square vanishes. On the other hand, this is the same thing as A nu squared. This is the same thing as nu sandwiched around A dagger A nu. And A dagger A is the number operator N, so this is just equal to nu itself. So we can summarize this by saying A nu is equal to 0 if and only if nu is equal to 0. Let me box that because that's kind of an important step in the logical derivation here. It's equal to 0 if and only if nu is equal to 0. If you do a similar analysis of A dagger, what you find is that A dagger nu is never equal to 0. It's always non-zero. This is assuming that nu itself is a normalized eigenstate of the N operator. All right. In view of this A nu statement up here, we can reformulate the theorem up above in the following way. We can say that if nu is not equal to 0, then A nu is an eigenket of N with eigenvalue nu minus 1. Let's state it that way. Because when we state it that way, it implies that nu has to be equal to an integer, which let's call it N now. Now that we know it's an integer, let's call it N instead of nu. How do we know that? Well, we do it by contradiction. We say, suppose nu is not an integer. Suppose nu is equal to 1/2, for example. So the capital N acts on 1/2 and brings out a value of 1/2. Let's suppose such a thing were possible. Now 1/2 is not equal to 0. So that means that A acting on 1/2 is not equal to 0. But by this theorem then, that means A acting on 1/2 is an eigenstate of N with eigenvalue minus 1/2. Right? But on the other hand, we know that the eigenvalues of N have to be non-negative, and so this is impossible. So we reach a contradiction if we assume that nu is a fraction, is not an integer. So therefore, nu is equal to an integer. If nu is equal to an integer, we don't have a contradiction because we can take the state N like this, and we can lower it step by step by applying the annihilation operators until we get down to the state 0. Then when we apply the annihilation operator to that again, we get a state, not the state minus 1, but rather just 0. It annihilates it all together and gives us the 0 state. And so the lowering stops at that point. So that's why the scheme works for the case of integers. So as a result of this, we now have the spectrum of the operator N, and it's equal to all integers, all non-negative integers, 0, 1, 2, and so on like this. And the spectrum of the Hamiltonian H is the same thing plus 1/2, so it's 1/2 3/2, 5/2, and so on, like that. All right. Okay, now then. So that's the essence of Dirac's algebraic derivation of the spectrum of the harmonic oscillator using raising and lowering operators. There's a few more comments to make here about the matrix elements of the raising and lowering operators. Based on what we've said so far, if I apply A, so let's do this. Let's get our eigenstates in like this, where n goes from 0, 1, 2, 3, and so on, with some arbitrary phase conventions, some phase conventions. The states are non-degenerate, but they're only determined to within a phase. And let's worry about the phases now. So we'll do this in the following way. If I apply the annihilation operator to the state 0, the answer has to be equal to 0. If I apply the annihilation operator to state 1, I have to get something proportional to the state 0. So let's call it C1 times 0. Let's apply A to 2, and we'll get C2 times 1, like this. It has to be constant C1, C2, and so on, like this, that make these equations true. Or more generally, I have A acting on n is equal to Cn times n minus 1. Now, if I square both sides, the left-hand side square is n A dagger A n, which is the same thing as just n itself, because what appears inside is a number operator. And that's equal to the square of the right-hand side. The cat n minus 1 is assumed normalized, so it becomes mod Cn squared. And thus what we find is that Cn is equal to the square root of n times a phase factor I'll call e to the I alpha n. If I then write out these lowering relations with these phase factors, what I now have is A acting on 0 is equal to 0. A acting on 1 is equal to e to the I alpha 1 times the square root of 1 times 0. A acting on 2 is equal to e to the I alpha 2 times the square root of 2 acting on 1, and so on down the line. Now then, here's what we will do. We will redefine the phase conventions for the excited states 1, 2, 3, and so on. We'll leave state 0 alone. We won't change its phase convention. That can be chosen arbitrarily. But once the phase for state 0 has been chosen, for the rest of them, we'll redefine them. And I'll do it this way. I'll write 1 is equal to 1 prime times e to the I alpha 1. And I think you can see that if I substitute this in over here like that, then I can cancel the e to the I alphas here. And then if we drop the primes, what we get is the formula that you know and love very well, which is that A acting on n gives me the square root of n times n minus 1. And I went through that because I wanted to show you that to be careful about this stuff, you need to worry about phase conventions. And this last step, what I've done is I've shown that phase conventions for the harmonic oscillator eigenstates exist, which cause the matrix elements of the annihilation operator to be real and positive. That's what's come out of this, you see. That's what that square root of n is. Moreover, it's worthwhile remembering that the phase convention of the ground state is arbitrary. But once that's been fixed, then those of all the excited states are linked to it in order to make this equation true. Now you can show, and I'll skip the details because it's all in the note. You can show that if this is true, then it's also true that A dagger acting on n is equal to the square root of n plus 1 times n plus 1. And again, this is a formula that you no doubt know because you've had it on exams, no doubt. This new formula, the lower one, does not require any more phase conventions, and that's a good thing because we used them all up in the first step. It's pretty clear that if the matrix elements of an operator are real, then the matrix elements of a Hermitian conjugate are also real, and that's what we've accomplished here. But this is explicitly how it works out, the real and positive, as you can see here. All right, so then gives us the usual formulas for the A's and the A daggers. All right, that's all I want to say about Dirac's derivation of the algebra of harmonic oscillators stuff. Is there any questions about that? If not, then the next topic is the Heisenberg picture, which is a very useful way of thinking about harmonic oscillators. Let's look at the Heisenberg picture now. So below this line, if I can spell it right, below this line is the Heisenberg picture. The Hamiltonian is the same, has the same formula as before, 1/2 x squared plus p squared. I'm not going to put hats on the operators to indicate operators, nor am I going to put H subscripts to indicate Heisenberg, but this is all going to be in the Heisenberg picture below this line here. If we do this, then the Heisenberg equations of motion are that x dot is 1/I times the commutator of x with h. And the commutator comes strictly from the kinetic energy. And if you work it out, it just turns into a p. And likewise, p dot is 1/I times the commutator of p with the Hamiltonian. And this turns out to be minus x. If I summarize them over here, I've got x dot equals p and I've got p dot equals minus x. So these are the Heisenberg equations of motion. These, of course, are operator equations. Now, let me draw a line and let's talk about the classical motion. The classical Hamiltonian has the same formula, but of course now the quantities in question are C numbers instead of operators. Classical equations of motion are x dot is partial of h with respect to p, which gives us p, and the p dot is minus partial h with respect to x, which gives us minus x. And so the classical equations are x dot equals p and p dot equals minus x. And lo and behold, they have the same form, exactly the same form as the Heisenberg equations of motion, but with a reinterpretation of the symbols. The symbols, of course, classically are C numbers rather than operators. Now that makes it quite easy to solve the classical equations of motion. It's just elementary solutions in classical mechanics. X of t and p of t turns out to be given by a matrix. It's cosine of t, the sine of t, minus the sine of t, and the cosine of t, multiplying onto the initial conditions, x of 0 and p of 0. This is the classical solutions, like so. All right. Now, what does this classical solutions look like? By the way, so maybe before I go on, let me just say that if you want the solutions of the Heisenberg equations of motion, it's the same solutions. All I need to do is just run through here and put hats on the operators. So it's x hat and p hat as a function of time is equal to this same matrix. I'm going to call this matrix R of t here for reasons I'll explain in a minute. It's equal to R of t times the x hat of 0 and p hat of 0. These are the solutions of the Heisenberg equations of motion in quantum mechanics, exactly the same form as the classical solutions. Right, now, allow me to continue for a bit with the classical solution. Let's plot the orbit in phase space and see what it looks like. So phase space is position x and momentum p like this. The Hamiltonian has contours which are circles. That's the orbit is a circle in phase space in these scaled units like this. So this is h equals 1/2 x squared plus p squared equals energy E. And this R of t matrix that appears up above is a rotation matrix in phase space. It rotates by an angle, rotates in the clockwise direction by an angle which is the time t. So that's why I call it R of t, because it's really a rotation. So that means if I have an initial condition here, which is x0, p0, I'm still doing the classical here because I'm below the classical line, if you can still see this. This is all classical. Then at a later time, and I've got x of t and p of t, like this, then the angle here is the time t. That's all it is. It would be omega t if we restored ordinary units, but that's what it is. So the orbit in phase space, the classical orbit is going around and around a circle, just like that. Okay. Now then, having done all that, let's go back to the Heisenberg picture in quantum mechanics, and let's take these solutions of the Heisenberg equations of motion here, and let's sandwich them on the left and the right by a state psi h of a quantum state like this. If we do, let me lift it up so you can see it. So you can see it here. This didn't come through looking very well. It's psi h. We sandwich it with a state psi h in the Heisenberg picture, converting these x's and p's at the initial and final times into expectation values. And so if we do that, what we obtain, and I'll give the summary down here, what we obtain is that the expectation value of x is a function of time, and the expectation value of p is a function of time, are equal to the same R of t matrix multiplied times the expectation value at 0 and the expectation value of P at 0. In other words, the expectation values follow the classical orbit. Now, we kind of went over some of the same territory not so long ago in connection with the Ehrenfest relations, and I pointed out that in the case of the harmonic oscillator and certain other Hamiltonians, the expectation values actually follow a classical orbit, and I'm really just repeating that here with the explicit example of the harmonic oscillator. But this gives you the picture of the orbit, and now you can see what expectation values do in phase space, pairs of expectation values of position and momentum, what they do in phase space in the quantum problem. In deriving these quantum expectation values, I did not make any assumptions about what the state psi h is. In particular, it does not have to be a wave packet or anything that you might think of looks like a wave packet. It could be linear combinations of wave packets, one here and one over in San Francisco. It won't matter. It could be something much crazier than that. It should be normalizable because we're talking about bound state problems here. But except for that, it can be any old thing. And this evolution of the expectation values following the classical orbit is still rigorously true. Okay, for the harmonic oscillator. Now then, we can also work with creation and annihilation operators. First, let me go back to the classical picture again. If I use the classical variable z, which I'll remind you is x plus ip over root 2, like this, and z bar was a complex conjugate of that, it's easy classically to work out the equations of motion for z, and you find that z dot is equal to minus I times z. And therefore, the solution is that z of t is equal to e to the minus it times z of 0. This is the classical solution on these complex variables here. Now, the definition of this complex variable z equals x plus ip shows you that apart from the square root of 2, that x and p are the real and imaginary parts of this complex variable. So that means the phase plane, which is the xp phase plane, can also be interpreted as the complex z plane. So there's a real part of z and the imaginary part of z, like this, or except for the square root of 2, this is the same thing as x and p here. So the orbit in this plane is still a circle, like this, and the evolution is the same as before, except if they call the initial condition z of 0 and the final condition z of t, like this, then the solution is that z of t, you can see it right up here, it's e to the minus it times z of 0. Well, that's just multiplying by the phase factor, which is the rotation in the complex plane, that's what phase factors do in the complex plane. So this is a reinterpretation of harmonic oscillator dynamics in terms of these complex variables. By the way, if we do the quantum problem in the Heisenberg picture, and we look at the evolution of the creation and annihilation operators, A dot has got an evolution, it's 1 over I times the commutator of A with a Hamiltonian. And if you work that out, that's equal to minus IA. And therefore the solution is that A of t is equal to e to the minus it times A of 0. And as far as the daggered part, it's just a complex conjugate of that. It's e to the plus it times A dagger of 0. And this is a solution of the Heisenberg equations of motion in terms of creation and annihilation operators. And you can see it's exactly the same form as these z formulas for the classical motion. All right, so this is part of the story about connecting the Heisenberg picture with the classical picture. In the case of the harmonic oscillator, you can see that formally they're almost virtually identical. Okay, are there any questions about that before I go on to the next topic? All right, the next topic concerns coherent states. The name coherent states isn't really a very good name because it doesn't really characterize what they are, what they're good for. Coherent states are good for at least 2 things, which I'll tell you about. One of them is that to some approximation, they represent the quantum state of laser light in quantum optics. It's an important topic in quantum optics. For reasons that I can't go into now, laser light is the quantum state of it is approximated by a coherent state. Let me just make this comment about it. We'll have to wait till next semester when we properly do photons. But let me just comment that if you think about a plain light wave or even a mode in a box, normal mode in a cavity, it's clear that it's an oscillatory motion. You've got electric and magnetic fields that are oscillating back and forth. And it's fairly obvious that it ought to be describable in terms of a harmonic oscillator. And this is exactly what happens when you do the quantum field theory correctly. And so that's why that's why the subject is coming up now in the context of harmonic oscillators. Right now, we're talking about mechanical oscillators rather than photons, but the mathematics is identical. A second reason for being interested in coherent states is that they're useful for understanding, they're used this way in the literature rather frequently, is that they're useful for understanding the classical limit of various quantum phenomena. And now let me explain how that comes about. Let me start with the ground state of the harmonic oscillator, size 0. I'll write it in wave function language. In Ket language, of course, it's just 0 like this. But in wave function language, if you normalize it, the wave function and everything is 1/π⁴ times e to the minus x squared over 2. And this is still using these dimensionless units that I've introduced. Now, this ground state wave function has the property that the expectation value of position and the expectation value of momentum are both equal to 0. And it also has the property that the dispersion in position is equal to the dispersion in momentum. Delta x and delta p are equal to one another and take on the value of 1/√2. The uncertainty principle for position and momentum says that delta x delta p is greater than or equal to h⁻/2, which in our units just becomes 1/2 since we're setting h⁻ equals to 1. This is true for any state whatsoever. But what we call a minimum uncertainty state is one where the inequality turns into an equality where delta x and delta p are equal to 1/2. And it can be shown, and it is done so in the notes, by the way. I didn't lecture on it because it's undergraduate material, but you can find it in the notes. The proof that the minimum uncertainty wave function is actually a Gaussian wave packet that's contained in the notes. So in any case, the fact that the delta x and delta p for the ground state of the harmonic oscillator are equal to 1/√2, the product is equal to 1/2, that means that this actually is a minimum uncertainty wave packet. Not only that, the uncertainties or the dispersions in delta x and delta p are actually equal to one another. So this is something that gives rise to what we call a coherent state. A coherent state is a minimum uncertainty wave packet in the context of a mechanical oscillator. It's a minimum uncertainty wave packet in which the dispersions in delta x and delta p are equal to one another. Now, this is something that only has meaning with respect to these dimensionless units that I'm using. Let's leave it at that for now, but we'll take this as a definition of a coherent state. However, it's not the most general coherent state because the expectation values of x and p are both equal to 0. In general, coherent states have different expectation values of x and p other than 0, and I'll get to that in just a minute. But in any case, what this is saying is that the ground state of the harmonic oscillator actually is a coherent state. Now we can visualize this coherent state in the classical phase space in the following way. The expectation values of x and p give us a point at the origin, but when we make measurements on this ground state, there are fluctuations in x and p, and those fluctuations are limited by the uncertainty principle, the delta x and delta p. Let's indicate those schematically by drawing up a circular blob here in phase space like this. And what this represents this is not anything precise. It's just a pictorial representation of what happens when you make measurements of position and momentum on this wave function. You get an average value of 0, but you get fluctuations in both x and p, which have some degree of a spread in there. And we know what the delta x and delta p are. In fact, if you want to, you can think of this blob here as occupying a Planck cell of area, because that's what quantum states occupy, is a single Planck cell. All right. Now this is the case where expectation values of x and p are equal to 0. What if we want other expectation values for coherent states? Let me draw the picture again on a new page because I want room to do it. Let's draw this here like this. This is phase space, x and p. Let me draw the ground state of the harmonic oscillator here as a blob like this. Let's suppose I want a coherent state that has a different expectation value. Let's say I wanted to have an expectation value of x equals, let's call it lowercase a, like so. Move this here to the location x equals a, like so. So in other words, suppose I want average value of x equals a, want this. Well, one of the ways to do this is to use translation operators. I'll remind you that our translation operators we discussed earlier in connection with the momentum, T of A was defined, this is in the one-dimensional case, was defined as e to the minus I times A times P hat divided by H bar, except here we're setting H bar equals to 1, so I'll write it as e to the minus I A times P hat for the discussion tonight. That's the T of A, and that's what that operator is. And T of A, what does it do to wave functions? We worked this out earlier. T of A acting on the wave function psi maps it into psi of x minus A. That moves the wave function forward. T of A acting on the corresponding momentum space wave function of P multiplies it by a phase factor, which is e to the minus IAP times phi of P. This phase factor is really the same thing as the T of A operator, except the momentum operator in the exponent P hat has been replaced by P, because in the momentum representation, P hat has the effect of just multiplication by the C number P, and that's just what I've done here. So this operator is easy to evaluate in the momentum representation. In any case, this is what the T of A operator does to both position and momentum space wave functions. Now, what does it do to expectation values, expectation value of X and expectation value of P? If I apply T of A to this, what you find is that the X expectation value gets increased by the displacement. That makes sense if you visualize what the T of A does to the wave function. It just moves it rigidly forward. It has to do this. What about the momentum expectation value? Turns out it doesn't do anything to that. X-based translations don't affect the momentum translation, the expectation value. It's easy to check this, but just to do the algebra to check that the T of A doesn't affect the P. In fact, let me just prove it for you. The average value of P, if I evaluate it with the momentum space wave function, is this. It's integral over P of P times the square of the wave function phi of P squared, like this. This is just doing it in momentum space. But T of A acts on the phi of P wave function and just introduces a phase factor. So when you square it, the phase factor drops out and the expectation value remains the same. In any case, this is the effect of the translation operator in momentum. So that means I could use a T of A operator here like this. Can you still see this above? Yes. I can use a T of A operator to move my coherent state from the origin to give it a non-zero expectation value of X, but it has not changed the expectation value of P. Suppose I want to move it up like this to a location to give it an expectation value of P as well. I want to move it up here by a distance, let's call it B, in momentum displacement. How do I do that? Well, I need to have, in addition to displacement operators in configuration space, I need displacement operators in momentum space. So let's do those. Well, it's going to work like this. Let me repeat the definition here. T of A in configuration space is e to the minus IA P hat, like so. Let's define an operator. Let me call it S of B. It's equal to e to the plus IB times X hat. This S of B turns out to be the translation operator in momentum space. And what does this do to wave functions? Well, compare what the T of A did to wave functions up here. Here it is. S of B acting on a wave function psi of X multiplies it by the phase factor e to the IBX psi of X. Whereas S of B acting on a momentum space wave function, phi of P, maps it into phi of P minus B, which means we rigidly move it forward in momentum space. I think you can see the kind of symmetry between these momentum displacement operators and the position displacement operators up above.
Sorry, how did you know that there's a plus in the exponent in the S and minus in the T?
Because I work out the details and do it. If you recall that the momentum operator in the configuration representation is minus IH bar ddx, whereas the position operator in the momentum representation is plus IH bar ddp. That's where the sign change came from. But you need to do the calculation. You'll find that's how it works.
Okay.
There's these characteristic minus signs that occur here. All right. So now if I have this S of B operator, then what I can do is, and then what does it do to expectation values? Let's put that down. X and P under the momentum displacement operator S of B, what happens to it? Well, nothing happens to the expectation value of X, but the momentum expectation value gets increased by B. So that means that I can make my coherent state acquire non-zero expectation value momentum by applying an S of B like this. And in this manner, we can reach a point of phase space here with coordinates A and B, and we can create coherent states that are centered on any expectation value A and B that we want. What about the dispersions? A coherent state is supposed to have these balanced minimum dispersions. What about them? If I have the dispersions delta X and delta P like this, and I apply either a T of A or an S of B, what you find is that they don't change, they go into themselves. And I'm not going to prove this, but rather let me just give a plausibility argument. If you took an ordinary probability distribution and you displaced it, what would happen is it would change the mean, but it wouldn't change the standard deviation. So that's why this X displacement up here changes the mean by shifts it by A, but it doesn't change the delta X. And likewise, the momentum shift changes the momentum expectation value, but not the delta P. So of course, you really need to do the quantum calculation. Let me just say it's straightforward to do it, and you can check these results are true. So what that means is that the coherent state condition that delta X equals delta P equals the minimum value of 1/√2 is not affected by either of these operators. And therefore, what we really are doing here by moving these coherent states around is we're populating phase space with genuine coherent states, but with different expectation values. All right, now then, there is, however, a problem with this. And that is, if I can go back to this picture here, and that is that why did I do the X displacement first and then the momentum displacement? Why didn't I go the other direction first and then go across with the momentum displacement that way? Are the answers the same? And the answer to that question is that no, the answers aren't the same. And no wonder, because T of A is a function of the momentum operator and S of B is a function of the position operator, and they don't commute. Let's check this and see here. Let's take psi of X, and let's follow this path first. We'll apply the T of A first and then the S of B. So if I apply T of A to that, this turns into psi of X minus A. And then if I apply S of B, this gives me an E to the I bx times psi of X minus A. Now, on the other hand, if I do it in the reverse order, I apply the S of B first. I get E to the I bx times psi of X. And then I apply T of A, and I get E to the IB times X minus A times psi of X minus A. And so what we see is applying T of A first, and then S of B second, which is what we did in the top row, versus applying T of A second and S of B first, which is what we did in the bottom row. The answers aren't the same. And to make them the same, I should multiply the second row by E to the plus IBA. So we get that, we get this identity here. This is a kind of a commutation relation or a non-commutation relation between these S of A and S of B and T of A operators. All right. Now, the way to handle this, the elegant way to handle this, is to don't use these position and momentum translation operators at all, but try to create a new kind of translation operator in phase space that goes directly from the initial point to the final point. The operator that does this is called a Heisenberg operator. And all this stuff with these operators is good practice in position, momentum, commutation relations, and so on. A Heisenberg operator, I'll call it W of AB. And the Heisenberg operator is given by E to the minus I A times P hat plus IB times X hat. Now then, these are the same exponents that occurred in the position and momentum translation operators, but they're combined up into the exponent. You might wonder, is this equal to E to the minus I A P hat times E to the I B X hat, which would be the product of the position and momentum translation operators? And the answer is no, they're not the same. This brings up a theme which is going to appear a number of times in this course. It's worthwhile pointing out now the issue that's involved. If you have numbers A and B, that is to say, if A and B are C numbers, then there's the obvious identity that e to the A times e to the B is equal to the e to the A plus B. This is that they're C numbers. But if they're not, if they're operators, then this is not equal to e to the A plus B in general for non-commuting operators. If the operators commute, then it's still true. But for non-commuting operators in general, this is not true. And so there arises, so this is something that we frequently want to do in quantum mechanics. We want to compose or multiply together two exponentials of operators, which however do not commute with one another. And so we can't use the simple C number formula. That doesn't work. There's something more complicated, and it's not e to the A plus B. So what is it then? What is it? In fact, the answer in general is complicated. It's related to some topics like Baker-Campbell-Hausdorff theorem that you may have heard about and things like that. But in any case, let's just say for now that the answer is actually somewhat complicated. And as I can see, we're essentially out of time now. I'm going to leave with that thought, which is that the place we're going to pick up next time in this progression of ideas is with dealing with at least a special case of how we can combine exponentials of non-commuting operators in order to create a single exponential of a single operator. All right, so that's all for tonight. Are there any questions about this? And when we get this worked out, then we'll have the Heisenberg operators. We'll have formalism for them, and then we can use them to define coherent states using Heisenberg operators, which is the way people usually do it. And we can talk about their properties, and that'll be the content of the discussion of coherent states. So to repeat, then, are there any questions about any of this?
Yeah, I'm thinking. Is this Heisenberg operator equivalent to translating a differential amount in X, then followed by a differential amount in P, and then a differential amount in X, and then P?
No, no, it's not. Well, you see, it would be a question of now you're creating a path in phase space, right? And so the answer to your question is that the result would depend on the path. Your little delta X's and delta P's are creating a path in phase space. So the answer depends on the path. Now, if you're asking me, suppose I make the path that straight diagonal line would be the same as W. I'm pretty sure the answer to that is yes, but I'm not totally sure because you may want to make the infinitesimal segments, not jaggedy, but rather, tangent to the, I'd have to think about it.
Yeah, that was the other thing I was.
But yes, indeed. And in fact, there's an interesting question as to what happens if you do this transport along a classical orbit, step by step. That accumulates a phase, and that phase is actually a version of the Bohr-Sommerfeld phase, as it turns out. All right, any other questions?
Is it true in general that when the WKB theory gives exact energy values, exactly when the expectation values follow classical orbits, or was that just a coincidence?
Yeah, that's a good question. It is essentially the same, although the condition for the expectation values to follow the classical orbits is that the Hamiltonian should be at most a quadratic polynomial in position and momentum. That's essentially if and only if condition for that. However, just because it's a quadratic polynomial doesn't mean that it has bound states, so there might not be any quantization condition at all. But yes, when there is a quantization condition, these quadratic Hamiltonians also give you the exact eigenvalues.
Okay.
Yeah, any other questions? All right, if not, I shall,
I have a quick question.
okay,
I think when we were talking about the translation operator, we had said that the generator of translations is related to like the linear momentum.
that's translations in X. Yes, the generator is linear momentum. That's right.
Is there like an analog for our SB translations and momentum? Is there?
Yes. The position is the generator of translations and momentum. It's complementary, you see.
Okay,
The position operator.
thank you.
Any other questions? Okay, then, so end screen share, and now we end the recording.